There, welcome to this video lesson on graphs of radical functions. And specifically in this lesson, we are going to focus on square root functions. And if you click on the practice set, we'll do a little bit of exploration into other kinds of radical functions. But the most common one that you would see in terms of graphing radicals would be the square root function. Please like this video if you find it helpful. Subscribe to the channel for more math help. Drop a comment or question to engage. I'd appreciate that. And check out the practice set for this lesson so that you can review and make sure that you're understanding the key concepts we cover. Now, if you've been following the channel, you know it's been a couple of weeks since I've posted. It's the holiday season and things have gotten really chaotic just with the holidays and with the close of the term at school with the students that I teach. So hopefully I can get the rust off and do this lesson in 1 or 2 takes. We'll see. Okay, so we're going to start by graphing by hand. And this is a review of just how we generate functions. We never want to lose sight of that. And so looking at this, we're going to just generate our table. And I know I'm going to be taking the square root of x. So while I can, pick any numbers I want, I could do this. Not all of these numbers are going to square root really well. And so what I'm going to do instead is just focus on numbers that I know I can take the square root of. Now, when it comes to our discussion of domain and range, notice that I'm not going to pick the square root of -1 because if I were to plug in the square root of -1, we are going to get an imaginary number, and that is not going to translate to anything on the graph of the real numbers, like our real Cartesian plane here. And so we're going to start with the smallest number that I can take the square root of, and that would be the number 0. So what we're essentially doing is we are plugging in 0, and we're saying, okay, the square root of 0 is 0. And so that means the point 0, 0 is on my graph of this function. Now I'll go up in things that I know I can take the square root of. So we've got the square root of 1. And so you can do this in your head. You could grab a calculator to do it, but the square root of 1 is 1. And so I go over 1, up 1. And so that point is on the graph. Now, if you're the kind that leaps to conclusions, you might say, oh, well, there we go. Except that looks an awful lot like a line, and we know that this is not the graph y equals x. And so I'm expecting this graph to do something a little bit different. Now, 2 would give me a number, but it's going to be a messy number, okay? So we're going to put that in there. We'll come back and revisit that. But the next number that I can take the square root of easily would be the number 4, because the square root of 4 is 2. And so we're going to try to keep this friendly for us. So I go over 4 and up 2. And what you can tell there is that the slope of this is decreasing. So it starts off kind of heading in that direction, but now it is not as steep. It's still going up, okay, but not as steep. And the next point, that would be a good square root, would be 9. Okay, so we'll take the square root of 9. So that's going to be over here, up 1, 2, 3. And what we can see there, oh, it disappeared. Let's try again. Okay, is that it is getting even less steep, continuing to go upward. Okay, so it's not like it's leveling off, like it's going to be horizontal. It's going to continue to increase, but is decreasing in steepness. And then the last one that we'll check out is 16. So of course, plugging in the 16 is going to give us the 4. So I'll come over here to 16, 1, 2, 3, 4. And we can see that that trend is continuing where it starts off and seems like it is getting less steep as we go. Okay, now just kind of coming back to the 2, this is for those of you that might struggle to like graph stuff by hands. I know sometimes my students, when I ask them, just make a table and see what the graph is, we kind of hit a brick wall. Can you pick a 2? Absolutely, you can pick a 2. But when you go to take the square root of 2, you do get not a nice number. So that number is some kind of irrational number. If I think correctly, it's like 1.41 something. Okay, doing that off the top of my head. And if I come over here and I look at where the graph is, yeah, like I would buy that it's like less than 1.5 there. Okay, somewhere in there, but you're going to have to estimate where that is, and that's fine to do. Just, we want to avoid that if we possibly can. Okay, and forgive me if I picked the wrong number there. I am winging it on that. Now, one last thing before we move on from what does the parent graph look like. When I introduce this to my students, one of the things that I point out is that square rooting, okay, so square rooting is related to squaring. Okay, they have similar names there. And so if I had the number 5 and I square it, I get 25. But if I have the number 25 and I square root it, I get 5. And so we've got this what's called like an inverse thing going on here where you can undo the operation. And so it is logical that the graph of the square root would be related to the graph of squaring. So the graph of y is equal to the square root of x is going to be related to the graph of y equals x squared. Obviously not the same graph because it's not the same operation, but it is a related graph. And just so you know, here's how it's related. If you were to graph that would be the graph of a parabola. Well, the graph of the square root, it's a sideways parabola, but you only take the top half of it. So what we're looking at there is actually the top half of a sideways parabola. And the reason we don't have the bottom half is that would make it not a function. But if you remember this, okay, so we're kind of going back, if you had y equals the square root of x squared. Let me do this. 25 is equal to x squared. Okay, and then you square root it. You got to do that funky little plus or minus. I kind of did that backwards, and I don't want to restart the whole recording, so just bear with me. Okay, let's do it this way instead. So if you had x squared equals 25, when you go to take the square root of that, you do have to add this plus or minus because there are 2 numbers that would give you that particular square, and it would be plus or minus 5, and that minus would be the bottom half of the parabola. Okay, it would be like this piece down there. We give you like the plus or the minus, but when we take a square root, we don't typically take plus or minus. Okay, we assume the positive, and that's what gives us this function that's like the top half of sideways parabola. So I know a lot of my students will sometimes confuse square rooting and squaring. Like they'll just say one when they mean the other because they are related. The graphs are related, and now you can see the algebraic kind of how they're connected to each other. Okay, so now that we've established the parent function, what we're going to do is look at our known transformations. So these are things that we have already covered. We've covered them in earlier lessons. Okay, so if you need to, you can go back and look at previous lessons on transformations. If I can find one, I'm going to go ahead and link it up there. Okay, that's I'll just kind of scrounge through my own playlist, see if I can find something. So there might be a link up there so you can go back and look at it. So one of these would be our vertical translation. So translation is the mathy word for a slide. So we're literally just sliding that parent function up and down on the coordinate plane. Typically when we do this, we do put the vertical transformation on the outside or like on the right end of it. Something I've noticed about my own students is they put a lot of emphasis on right and left in the equation, which is something math teachers do not tend to do. We look at the operation that is happening, not where it's written. And so you could have f of x is equal to the square root of x plus 4, but you could just as easily switch the order of that and say 4 plus the square root of x. So the reason for that is the commutative property. It's like 3 plus 5 is the same as 5 plus 3. The order does not matter. And so you can switch it. And with radical functions, this is maybe the first spot where you actually will see that done. And it's a neatness issue because somebody is going to do this. Okay, and it's going to leave you wondering, is the plus 4 under the square root or not? Like, what did that person intend? Did they intend this, where the plus 4 is clearly not under the square root, or did they intend this, where the plus 4 is under the square root? We want to be really clear about that. Those are two totally different things, okay? It's the order of operations. What am I doing first, the square root or the adding? And so to avoid that confusion, you will often see this, or maybe not often, but like decent amount of time. Okay. Somebody will take that and just move the adding over to the other side. So there's no question about it. Okay, we're not going to have that problem. And that is the reasoning behind it. And you don't want to let that throw you off. Okay, that is just an invocation of the commutative property. And so you could have this first one, which would slide it up 4. Okay, and this would also be up 4. Now, if you subtract a number, that's going to take it down. So this would be down 3. And if you switch the order, okay, notice that the negative goes with the 3. This is the operation that's happening between them, and what is being added is the negative 3. This is where and if you've watched these videos, you have heard me say this, that my teacher would not let us write subtraction. He made us write stuff as plus a negative. And so we could see, oh, like that negative is attached to the 3, and that is adding. So when you switch the order, you don't want to do this. Okay, that's totally different. Subtraction is not commutative. So the negative has to come with the 3, and the operation between them remains an adding operation there. And so that would be a down 3. You're going to look for the sign in front of the number. That tells you whether or not you are moving up or down, not the sign of the square root. Okay, that's going to tell us something different. So what I did was I went ahead and graphed those so we could see them. So this is my vertical translation up. And so if you remember, this was like our parent graph was like right there, kind of anchored at the origin, and watching that endpoint is a good way to determine the translation. So you can see that endpoint slid up 4 units, or this one here, the endpoint slid down 3 units. So that is our vertical translations. And I do want to address that, moving things around, because sometimes moving things around with that sign can be a little tricky. Then we have our horizontal translation. So this is sliding it left and right. And this is one that is backwards from what your intuition says. And again, if you need to go back and look at a lesson that focuses on these transformations, like how we came up with them, why we know what they are, we know that adding or subtracting inside the function as opposed to outside the function does control our left and right. And so you would think that a plus sign would make it go to the right, but it does not. It actually goes left 4, and this would actually make it go right 3. And if you like question that, you could go ahead and just do some, build up the points or build the table. So I'm just looking at this. If I plug in a negative 4, okay, we'll just do the top one here. Negative 4 plus 4 is 0, and the square root of 0 is 0. And so when x is negative 4, the y coordinate is 0. And if you think about negative 4, this is actually moving left, not moving right. Okay, so negative 4 is to the left. If I plug in, what do we want? Like a negative 3. Negative 3 plus 4 would be positive 1, and here's our 1. If I plug in a 0, I guess is the next one. 0 plus 4 is 4, and the square root of 4 is 2. And if you compare this set of numbers right there with our set of numbers when we were building our table, you can see like, okay, those y coordinates are exactly the same, except now everything on my x's is actually moved to the left, not to the right. So let's take a look at those graphs. And here they are. And notice again, it is actually to the left 4, and this one is to the right 3. And you can use Desmos, you can use any kind of graphing utility to confirm that if you were blanking out on it. But it is one of those things that after you look at it for a while, you do want it to be intuitive. You have looked at this enough to know, yes, this is the direction that it goes. It doesn't matter that your intuition says, oh, plus should go to the right. It actually does not go to the right. And you can confirm that by plugging numbers in and looking on the table and then comparing the ordered pairs on the table to the graph. Okay, you can back it up to that step. We just don't want to have to do that all the time. So we have our up and down, and we have our left and right. Next one is our stretches and compressions. Sometimes this is called a dilation. And this, if the number in front of the parent function was a 1, okay? So it was like 1 square root of x. Remember, we're multiplying there. And so if I go greater than 1, we stretch it. Okay, and if we go less than 1, we are compressing it. It's like we're pushing it down. And this is specifically a vertical stretch and compression. You can do horizontal stretches and compressions as well. They are not as common. Sometimes they are reserved for, say, a college algebra class or a pre-calculus class. Once you kind of got your head around the vertical ones, in terms of what the graph looks like, there's a lot of similarities, like where a vertical stretch can look like a horizontal compression. And so I tend to avoid that. It could be just kind of focus on one of them. And then if you've got that skill set in place where you can build a table and look at it, or you've got a graphing utility to look at other transformations, you can kind of figure out the other ones as needed. But let's take a look at this one. Now, this one I did put in black. I put the parent because dilations, you're stretching and compressing, is harder to see when you're translating it or reflecting it. You can very clearly see, well, yes, this graph went up. It's a little bit harder to see if it got stretched without something to compare it to. And so that black one in the middle, that was our original one. So you can kind of follow, like we got the 0.11, we've got the 0.42, we've got the 0.93 right there. And this one is multiplying it by 2. And what might be interesting to look at is you can see how the y coordinates get multiplied by 2. So all of those start at the origin 0, 0. But if you look at where that point is at the point 1, 2, as opposed to the point 1, 1. Okay, this right here is at the point 4, 4, as opposed to the point 4, 2. And you're actually doubling the distance. Right here we went up 3. This one's going to go up 6, and so you'll have the 0.96. So what you can see from the ordered pairs, okay, so if I come over here and we look at the parent and then we look at the new one, okay, if we have 0, 1, 4, 9, the original was 0, 4, 2, 3. The doubled one goes 0, 2, 4, 6. And so you can see, like, yes, we're multiplying it by 2 and we're like stretching it out. Now with the 1/2, okay, that's the graph in pink. When you get to the 1, no, well, 0, 0 is the same. Okay, it's actually only up halfway. Instead of a 2, it's only gone up to 1. Instead of a 3, it's actually at 1.5. And so that is your compression. So it's like pushing the graph down instead of stretching it upward. Those are not as common, and what I usually expect my students to be able to do is to just say, okay, this is a stretch or this is a compression, not necessarily sketching it accurately, and if so, like I might provide them with the table to start with that. Not as common, but that is a transformation that we've covered. Now, this last one is a reflection over the x-axis. So what this does is if we look at our, again, our like kind of key points, so we'll kind of do these ones where we had 0, 1, 2, 3. The moment you make it negative, negative 0 is just 0, but now you have negative 1, negative 2, and negative 3. And so what that's going to do is like flip the graph down. So you're at negative 1, negative 2, and negative 3. So you got the 0.9, negative 3 instead of the 0.93. And what that is a mirroring of the graph over the x-axis. So we have seen that before with that reflection or flip. I will let my students say flip. I think, but you can use both words. All right, so what does that leave us with, like, new stuff? So new stuff with this family. Now, I don't want to imply that you can't reflect parabolas this way. You can, but to see the reflection, you actually need to do some kind of translation, a horizontal translation, in order to see it. And that gets a little bit messier. So sometimes we don't do that in Algebra 2. We kind of save that for a later math class. But with radicals or your square root functions, this you actually can see. So if we explore this with our table, okay, so we'll do, x is 0, that's fine. So you have f of 0, you have the square root of negative 0, which is just like 0. Okay, so it starts in the same place. But if I try to put in x is 1, all right, because of that negative, now I'm like kicked over to these imaginary things. So it means it doesn't go over to the x is 1. But what I could do is put in a negative 1. Okay. And what that does is it's going to double up the negative, because I had a negative in my function, and now I'm going to bring in another negative. So that makes that the square root of 1. And so what is happening here, so we could do this with negative 4, and then again with negative 9, okay, and so forth, is we have sent all of our x coordinates over to the left instead of the right. So let's take a look at the graph. All right, there it is. So now we still have the 0, 0, but now to get that 1, now I'm over at x is negative 1. I am over here at x is negative 4, and right here at x is negative 9. Why? Because I had to bring in a negative in order to combat, so to speak, or cancel out the negative that was already there. So this is a reflection over the y-axis. Remember that our parent function is going that way. And that is a new feature of this particular family, where you do not have to have some kind of translation in order to see this reflection. So in terms of new material, like, there you go. All the rest of that we've seen before, but we're maybe exploring it a little bit deeper or refreshing it if it's been a little bit since you've seen it. Okay, so we have that. Okay, I've got to start this slide over again. That's all right. I clicked through it. All right, so this is where it might mess with you a little bit. So you're looking at this, somebody says, okay, describe the transformations. Like, okay, I can describe the transformations on this. So you think, all right, we just covered this, right? So this is a flip or a reflection over the y-axis. And then you see the +4, and you're like, all right, I know what that does. That goes left 4. And then you go to Desmos or your graphing calculator, or Graph, wherever you're going to generate a graph, okay? You go to ChatGPT and say, graph this for me. And then you see that. You think, oh, that is not what I expected to have happen, okay? Now, did it flip over the y-axis? Yes, and I can tell that because it is heading in this direction, but it clearly did not slide that anchor point or that end point to the left. It went right, and so we're come over there. Now, if you're taking notes, pause the video, make sure you update your notes. So if you confidently wrote that down, you don't want to leave that in your notes. Okay, so that went to the right. So there's a couple different ways we could explore this, and I am not sure what I did the last time I was on this slide. thought I had another slide with this, but maybe I did not. So I'm going to write down here. So here's what's happening algebraically, and then we'll take a look at the table for this. What essentially, like, we want to think about this is we're going to factor out that negative. It has to do with the order that you do the transformations in. So if I factor out a negative x, factor out the negative leaves you with x, and then that positive 4, we would factor that out, and that becomes a -4. So if you're like, what did she just do there? Take a moment and kind of redo this backwards, okay? So you've got negative x, and then the negative of a negative would be a positive, giving you that +4. And now you can see, okay, if we write it that way, then we've got the transformation, or the slide to the right instead of the left. So what it has to do is it has to do with the order that you're doing things in. So if you were to look at this one, okay, and think about it this way. I just had a notification come through. So maybe you thought of it as, okay, so we take our parent function and we go left 4 like that. Okay, that was not the best one. That you can't really see the curve on that. Then again, like that. And then you do the flipping. So now you're going to take this and reflect it over here, okay? And you're going to like spin the whole thing around so it looks like that. So you could like slide it to the left as expected, but then when you do the flip over the y-axis, it's going to end up flipping that anchor point over to the other side. Or if you write it this way is like doing it like so, which it might be a little bit easier. On this one, you're going to flip it over the y-axis and then go to the right 4 like so. You could also reason this out by looking at like your ordered pairs. So you might think, okay, well, when x is 0, that's going to give us the 2, right? It's going to be the square root of 4. And then you can kind of think about, all right, so -4 plus, so if I put in like -4, x is equal to 4, okay, then it would be -4 plus 4 is 0, and the square root of 0 is 0. And you can see like, okay, like my ordered pairs would end up over to the right, not to the left. So that is like a tricky thing. Do slow yourself down when you're looking at that. Again, it does have to do with the order that you're doing the transformations in. And as a backup, you can go back to that table and start plugging in some values. Okay, start plugging in some values, and then you can plot the points and see where the graph winds up. Now, sorry, this is going to be like a long lesson. We are almost done, though. I promise there's only 2 more slides. So Desmos is a great tool for verifying domain and range. So now, if you wanted to do this one without using Desmos, I always recommend using your transformations. So we've got, what do we have going on here? We have a flip over the x-axis, and then we're going to go up 3. And so this is going to look something like this, like that. And you want to focus on that end point there. And I can see, all right, well, it looks like my domain is going to be everything greater than 0. And my range is my y's, and it's heading downwards. So we'll do like less than or equal to 3. Now, here's where Desmos can come in handy. You know, it would be awesomer is if I had the same equation in both places. All right, well, like, this is like what we call pivoting. So I hope you enjoyed that example. Let's do another one. Okay, so this one is a flip over the over the y and up 3. And so when we look at that, we're going to be flipping it over the y, which is going to send it that way. And then we'll go up 1, 2, 3. So it looks like that. Okay, same anchor point at 0, 3. And so my domain this time would be x is less than or equal to 0, because we're going like to the left. And my y's, this time the y's are going up, so y is greater than or equal to 3. So sorry about that detour right there. If you look over here, what Desmos is awesome with is verifying that. So if you do this like by hand, you're like, okay, I think that's what my domain and range are. Then you can use Desmos. If you do this correctly, what you should be able to see is this highlighting. So if you've got the domain correct, x is less than or equal to 0, you can see that blue highlighting, and the graph is completely inside the blue highlighting. Y is greater than or equal to 3, that's highlighting upward. The two shaded regions should intersect right at that endpoint. Okay, so that should be the endpoint of my graph, and the graph should be entirely in the region of overlap, meaning I've captured both the domain and the range. If you are looking for interval notation, you've got your negative infinity there and your 0. So this would be negative infinity to 0. Make sure you do include the endpoint, because x can indeed be equal to 0. And on my range, that is infinity right there, and so this would be 3 to infinity. Make sure you use brackets around the endpoints and parentheses around your infinities, and that you make sure that you always have the smaller number on the left. Let's see if the last one I managed to match them up. All right. So this one, we've got, this should be going right 4 and up 5. And so if I sketch my graph real quick, like we have right 1, 2, 3, 4 and up 1, 2, 3, 4, 5. And this has no reflection, so it goes in that direction. And I did that very sloppily. I made it look like it kind of curved back down, which it does not do. So my domain is moving to the right, so that would be greater than or equal to, and you kind of look and say, all right, where is my x? That's at 4, and my range is going up, so that would be y is greater than or equal to 5. So let's go check our Desmos graph. And here we have x is greater than or equal to 4, and you can see the shading on the blue. Y is greater than or equal to 5, so you can see the shading in the green, and the entire graph is captured in both the domain and range. Therefore, I know that I have done this correctly. If you are looking for your interval notation, right, remember your infinity. My apologies for my infinities. Are pretty terrible. So you're looking for where the graph is, and this is the point 4, 5 right there. And so this is starting at 4 and going to infinity. So 4 to infinity. And this is starting at 5 and going to infinity. Take each problem as it comes. Please avoid trying to look for like, well, if it goes this way, then I put the infinity on the right. Like, no, just look at the graph, look at like, where is my shading, and state your interval. Yeah. Okay, so that is a longer lesson, I am aware. Please don't forget to like and subscribe if this lesson was helpful, if it kind of cleared up some stuff about transformations. Engage by commenting below. Let me know what you thought. If you want to criticize me for having a mismatched graph, you might hurt my feelings, but go ahead and do that. And check out the practice set for this lesson to reinforce the concepts that we went over, and I will see you in the next video.